Hello, in this short video I will explain the effect of dissipation on the topology of a spin 1/2. To illustrate this notion, let's just consider a single spin 1/2 in an external magnetic field with this Hamiltonian, where the sigmas are the standard Pauli matrices and D denotes the external magnetic field in 3 dimensions, parameterized by the angles theta and phi, and we also allow for the possibility of an offset h0 along the z direction. For any given value of theta and phi, one can find the ground state of the system and represent it by its block vector, defined in this way. Let's first consider the case h0 equals 0 and plot the ground state block vector when theta varies. This is shown here on this plot. The black dot denotes the position of 0 magnetic field, and the red circle shows the evolution of the magnetic field when theta varies from 0 to 2 pi for a constant value of phi. On top of that, we draw the orientation of the ground state block vector for several values of the external magnetic field. For theta equals 0, here, the ground state block vector points upwards, and it progressively rotates when theta changes. At theta equals pi, it points downwards. The important information is that in total the ground state block vector wins once along the dotted circle when the magnetic field wins once along the red circle. The situation is similar as long as h0 is smaller than h. And in that case, the block vector is no longer perpendicular to the red line, but still the ground state block vector wins once around the dotted circle when the magnetic field wins once along the red circle. The situation is very different if h0 is greater than h. In that case, the ground state block vector does not scan the whole sphere, the whole dotted circle, when theta goes from 0 to 2 pi. On the contrary, it goes back to its initial orientation without passing through the south pole. This discussion illustrates the existence of an invariant integer describing the topology of the ground state manifold under the variation of a periodic parameter of the Hamiltonian. This so-called Chern number is very important in condensed matter systems. This global topological invariant can be related to a local geometrical quantity, the Berry curvature, which describes how the ground state of the system evolves for small variations of theta and phi. The question that we ask now is the following. What is the effect of dissipation and decoherence on these fundamental topological and geometrical properties of the system? In particular, we investigate the effect of an external ohmic bosonic environment. This model is interesting because it displays a quantum phase transition to a polarized phase when increasing the coupling with the environment. More precisely, at alpha around 1, where alpha denotes the strength of the coupling with the environment, the spin gets polarized either on the north or the south pole by analogy to a classical spin with only 2 possible orientations for the spin. And from a topological point of view, this seems to be a very different regime where we only have 2 accessible points for the ground state block vector instead of the whole sphere. To summarize our findings, we show that the topology of the system is preserved as long as alpha is smaller than 1 before the quantum phase transition. And we also show that the Berry curvature is related to the magnetic susceptibility of the system. And interestingly, it diverges exactly at the quantum phase transition, alpha equals to 1. We also investigate realistic protocols to explore these effects in experiments based on time-dependent magnetic fields. So this work was done in collaboration with Antonio Sclocci, Peter Horst, and Karin Lehur, and it was published in this recent publication. Thank you very much.